Hello, we're going to check out another AP Physics C free response question where I like to call these linearization problems. It seems like every year they got one of these on the mechanics test. So basically, they give you some experimental data, and you're supposed to adapt that data so that you can plot a set of data that's linear, and the slope is going to be some constant that you're looking for. And they can be any type of physics relationship. In this particular one, we're going to look at some rotational motion and figure out the G for the free fall of gravity. So here we go. So we got a rod, length L, mass M. It can pivot freely about this point here. We're going to drop it from this position A, and it's going to swing down to position B. Okay, and they want us to use calculus to figure out the moment of inertia is this much. So here we go. Okay, so this is our equation for moment of inertia, and we're going to calculate the effects of all the mass on producing a resistance to rotation by going from this end, we'll call this side position 0, all the way out to the end to distance L. And we know as we go out further and further, each little chunk of mass produces more and more resistance to angular acceleration because it's related to r squared. Okay, so a little piece of mass here is not going to produce as much resistance as a little piece of mass here, and we've got to account for that using this equation. So our big thing is we're changing our distances, but it's related to dm, so we need to get rid of this dm and get it in terms of position. So we can integrate from 0 to L for this integral. And so to do that, we do a little density ratio here. So a little chunk of mass, which we could say like is a little chunk here. This little piece here is a little dm. Okay, and we can have those little chunks all along here. Is going to be a little chunk of dm compared to a little step across in the r direction. Let's call this the r direction. Okay, is going to be equivalent to the whole mass compared to the whole length in the r direction. And then so from here we can say, hey, I can substitute out my dm by saying it's equal to the whole length, the whole mass compared to the whole length times dr. And so we can replace that in here. Okay, now I have substituted in this stuff, that density ratio for the mass, and now I can go ahead and get my answer. Okay, and so when we run that out, we're going to bring out the constants out in front. Nothing happens then when you do the integration. And then when you integrate to r squared, it becomes r cubed over 3. Evaluate it for your limits, so all the way from the hinge out to the end. You get something that looks like this. 0 cubed is just 0. So that simplifies to this. We can cancel out an L on top and bottom, and we get our answer, which matches this. Okay, on to part B. Now it says the rod is fixed at one end and allowed to fall from the horizontal position A through the vertical position B. Part B, derive an expression for the velocity of the free end of the rod at position B. Express your answer in terms of M and L and physical constants as appropriate. Okay, so let's just look at what we got here. So it's going to go from up here. So I'm going to say that I'm going to define this as my 0, because the center of mass is in the middle, and it's going to end up going to this height. So I'm going to define this as the 0. This is my positive direction. Therefore, up here, when we first let go, I have potential energy due to gravity initially. And down here, it's going to be swinging. And so I'm going to say it's got kinetic energy rotational I'm going to define this as an isolated system. I don't have any force here that's doing a displacement on this. I do have a force here on the axle, but this object is not displacing where it's touching there. So this is an isolated system. Essentially, all my potential energy is going to turn into kinetic rotational energy. So let's go down here and write in such a thing. So I'm going to go ahead and start by saying, hey, I'm going to define this as an isolated system. Initial energy equals final energy. I'm going to add in some more detail there. My initial energy was gravitational potential energy, and it turns into rotational kinetic energy in the end. I can go ahead and do my next line here. So that's going to be big M G, and that's going to be, well, how far does it fall? If this is L all the way out to there, and this is L here, this is going to be just a half of an L from here to here. That height change for the center of mass is going to be L over 2, half the length, right? So I come over here, and I'm going to say for my MGH, it's going to be, I start having an initial height of L over 2. Okay, and then that's going to all turn into rotational kinetic energy, which is 1/2 I omega squared. And please, just a heads up, you need to anticipate for part A, you're probably going to recycle that answer down into part B or C stuff. So we have the moment of inertia right here, and so we're going to end up putting it in right in this spot. Okay, so I have a couple little things we're going to do here. So we're going to do a couple little changes here. First thing I'm going to say is I is equal to ml squared over 3. And also I'm going to say omega. So whatever this omega is, that's going to be related to the speed of the end of the rod by the tangential velocity divided by L. Okay? So however fast this thing is rotating by V equals omega R, okay, we can take this rotational speed and multiply it by R, and we can get the tangential speed. So at the end here, it's going to be the speed of this stick when at the bottom. It's going to be proportional to how fast this is rotating and how far out we are along this stick, and we're at the very end. So I'm just going to reorganize this to say basically V over R, and in this case, R is L. Okay, so that's how I get this. And we can plug in and rewrite this. Okay, so we get this equation now, and I can send some stuff on vacation. All right, have a good vacation. See you later. Nice hanging out with you. And what? We got some, this, I'm going to get rid of this and just distribute it here. Okay, and so we can see we're going to get rid of some of this stuff, and we can rewrite in our final answer for V. Okay, so this is kind of messy, so I'm just going to rewrite it again and see what I have. Okay, I'm left with all this stuff, and I isolate for V, and I get V is equal to the square root of 3GL. So there's our answer for that particular part. Okay, and just to recap, I call this a linearization problem, and you can always recognize them because they'll have a table that has a few values you need to fill in, and they will have a giant graph that you need to fill in. Okay, and just right away you should anticipate, hey, this is a linearization problem. I'm going to have to find some kind of a relationship, and I'm going to have to make some kind of graph, and probably for a constant like g or something, you'll have to end up linearizing for. So here's the part where it starts looking like a linearization problem. So it says here, an experiment is designed to test the validity of the expression found in part B. A student uses rods of various lengths that all have a uniform mass distribution. The student releases each of the rods from the horizontal position A and uses photogates to measure the velocity of the free end at position B. The data are recorded below. Okay, so basically they're going to take this situation and they're going to vary the ingredients of this. So they're going to change, like for different lengths and different masses, drop these sticks and measure how fast it's going here at the bottom with a little photogate, which basically senses how fast something passes through this little motion sensor. Okay, and they're going to collect all that data. So they took sticks of different lengths and plugged them in there and found the velocity for it. And so we want to use this data somehow. So for part C, they say, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate the numerical value for the acceleration due to gravity, g. Let's go ahead and circle this. So we want to solve for this thing. Now, life gets a lot easier if you just anticipate you're going to recycle stuff down. So we just solve for part B. There's our g right here. Right here. So what you're going to do is you're going to take this expression and you're going to solve and isolate for g here. So let's go ahead and maybe do that. So I'm actually just going to take this little piece right here and solve for g from here. So we got something that looked like g L is equal to v squared over 3. Okay, we want to solve for g, so I can then say, hey, g is simply equal to the ratio of the speed squared compared to 3L. And that's going to be what I'm going to use here, and I'm going to say, hey, this top part is going to be my rise of a graph, and this bottom part is going to be my run for a graph. And this is exactly what I would write on the test. Okay? And so when I go to graph if I graph v squared and 3L stuff, it should produce a straight line here that's based upon 3L being my horizontal axis and v squared being my vertical axis, and the slope of the straight line is going to be g. Okay, so my horizontal axis needs to be 3L stuff, and my vertical axis needs to be v squared stuff. And that slope is going to be my g. And once again, you'll typically take whatever expression they have you make up here, and you'll adapt it to solve for whatever the constant is they want you to find. And interestingly enough, this is how you can find the constant for any situation, and kind of interesting. So use the remaining rows of the table as needed to record any quantities that you indicated that are not given. Label each row and include the units. Okay, so we're going to go up here and basically fill in this table. I'll do that now. So, well, let me just show you what I'm going to do. So we're going to do 3L stuff. The units are just meters still. And down here it's going to be v squared, which now we've squared something, so it's going to be meters squared per seconds squared. Okay, and then I'm just going to run through these my calculators efficiently as I can for this timed test. Okay, so I've gone through and ran these numbers through here. So I just took this one and I multiplied by 3 to get this one. I just took this one and squared it to get this guy. Okay, and I did that all the way across here. It's a little bit time consuming, but just pump it out as fast as you can. Now we can go and plot these things on our graph below and we'll have it. So it says here for part D, plot the straight line points on the grid below, clearly scale and label all axes including units as appropriate, draw a straight line that best represents the data. Okay, and so I just rounded somewhere close to how many digits they're showing here. And please, when you're graphing this stuff, this is a time test. Just give enough information that they can follow along with what you have. You don't want to label every little line on here. And what's most important is you show the process, you know what you're doing. It's not necessarily the accuracy of this graph that's particularly important, because after all, in real life, you would just plug this stuff into a computer and press go, and it would give you your best fit line. So show the process. Okay, so I'm gonna go ahead and set this up, and I'll tell you what I'm doing as I'm going. Okay, so I'm plotting v squared for the vertical axis and show the units in parentheses. 3L for the horizontal axis and show meters for in parentheses for the units. And for my v squared stuff, my vertical axis, it looks like it could just go by tens, and I could have a good spread. So I got 5 lines here, so 10, 20, 30, 40. I should be able to use the bulk of the area with that. And for my 3L, it looks like it goes up to almost to 5, and I got 5 lines. It looks like it kind of is nicely distributed in there, so I'm going to go ahead and go by ones. 1, 2, 3, 4, 5. And now I'm going to just go through here and plot them roughly to the right spot, and we're on our way. So don't stress too much. Just get roughly the right stuff down there. So I'm going to go ahead and do this now. Okay, and so I went through here, and for each combination, I went and plotted it roughly on here, and it's looking nice and linear to me, so we're off to a great start. And once again, I'm not trying to be overly accurate, I'm just roughly getting these points on here. So we're down to part D, plot the straight line data points on the grid below, clearly scale and label each axis, including the units as appropriate, draw a straight line that best represents the data. Okay, so I put my line on here, and I know by the format here that it has no vertical intercept, so it has to go through 0. So I'm going to pick here for my straight edge, and then just go roughly through the center of the data. It does not have to hit every point. It just needs to go through the middle of the data. And so you can see that some are a little bit up and some are a little bit below, but that's fine. Just do it roughly to scale here. Part EI, it says, using your straight line, determine the experimental value for G. Okay. Okay, so I'm just gonna go on here and I just pick some points that just nicely follow my line. I know that it goes through 0, so I'm gonna pick this as a point. And I'm gonna pick, it looks like it goes through exactly one of my data points. So I'm gonna pick that as my point. I'm gonna draw my rise and run on here. And then I'm going to go down here and just restate my equation and say, hey, this is the rise, this is the run, put in the numbers for what that was. And so these just happen to be nicely this exact data point, so I didn't have to go do a whole lot of work, which I'm kind of looking for something like that. And 27 over 3 is 9, and it should be meters per second squared. Yes, this is meters squared per second squared, and divided by meters, we cancel out one of those, and you get an acceleration set of units. And so yeah, just go and pick a point that works kind of well. You probably will usually have a 0 intercept, and just take 0 out to some point, rise over run out to some point that goes exactly on your slope of your best fit line, and just throw in those numbers and you got your answer. And the last part here, it says, describe 2 ways in which the effects of air resistance could be reduced. Well, you could say, I don't know, let's get rid of the air, I guess. So do experiment in a vacuum. I can never spell correctly. And the other thing you could say is maybe make rod aerodynamic, or you could say maybe make the rod more massive, because mass will tend to resist the acceleration put on it by the air resistance. So anyways, something like that. But anyways, that's kind of pretty simple to come across. The big part of this is knowing how to linearize a set of data for some kind of relationship. Once again, you'll always see, you can recognize it. You'll see this table with empty slots there, and then you'll see a big graph like this, and just right away you should anticipate the following things. I'm going to find some kind of relationship. I'm going to be solving for some constant in that relationship. I'll have to like reorganize it so I have that variable, that constant isolated by itself, and then I'm going to have rise over run stuff. These are going to be my vertical and horizontal axes, and I'm then going to fill in the table, and then I'm going to plot, find the best fit line, show the process of how you do this, rise over run, plug in those values, and you got your constant there. Okay, I hope this is helpful, and hope you can knock one of these out if you see it on the AP exam.